So don't forget to get you a little 3x5 card or something like that. Like I said, these important formulas you really need to know very well. In fact, I even rewrote my card because I thought it was a little bit sloppy. And when I rewrite it, it helps me memorize it even more. So this is what I have on one side. And then we've got the Pythagorean identities on the other side. Pretty soon this card will be full. But not every formula that we cover in this class do you have to have memorized. Just the most important ones, I'll point that out and add it to the 3x5 card. Okay, then on to section 2.1, of course, trig functions. And you may remember acute angle, that means angles less than 90 degrees. So for example number 1, suppose that you have triangle ABC with angle C being the right angle. And then suppose that side A is equal to 4 and side B is equal to 8. Then, well, I'm going to start drawing the picture and then write the rest of the question. So you've got this triangle ABC, and this is the right angle, so that's C. I'll call this angle A and this angle B. So across from angle A is side A, so this one is 4 meters or inches. Across from B is side B, so this is 8 meters or inches. And then this would be side C. So the first thing we need to do is solve for C using the Pythagorean theorem. C squared is equal to 4 squared plus 8 squared. That's going to be a 16 plus a 64. Now 16 and 64, that adds up to 80. And then take the square root, and the square root of 80, that could be simplified. Because I'm pretty sure that 80 is 16 times something. 80, is it divisible by 16? It's 16 times 5. First guess, first guess. So then, take the square root of the 16, that's a 4. And then the square root of 5 just has to stay as the square root of 5. All right, now find what is sine of A what is cosine of B. Okay, here we go. So, as you may remember, sine is opposite over hypotenuse. So when you're doing this, make sure that you look at the angle it's talking about, angle A, and then go opposite of that, 4, over hypotenuse C. So that would be 4 over the C, which is 4 radical 5. Or in other words, sine of A is equal to, when you reduce, the 4's will leave a 1 on top and then square root of 5. And unless you're specifically told to rationalize the denominator, you don't have to. You can leave it like that. Now, what about cosine of B? So then, I think, through my memory, what's cosine? It's adjacent over hypotenuse. The first thing to do is look at what angle is being talked about, B. Sorry. So opposite would be 8, adjacent would be the 4. So the B is right next to the 4, it's adjacent. And so cosine is adjacent over hypotenuse. So adjacent is 4 over the hypotenuse. Oh, déjà vu? What is that, the same answer? Yep, they are the same answer. So notice in order to get the same answer, I have to switch the angle. One of them was angle A, and the other one was angle B. Both of these are acute angles. They both have to be less than 90 degrees. Since this one is 90, that means angle A and angle B have to add up to 90. That means each one is an acute angle. And this is one of the points of this section. These are called cofunctions. So let me get a new piece of paper and talk about that. So if you have angle A plus angle B equals 90 degrees, then angle A and B are complementary. They complement one another. Not complement as in, hey, that's a nice degree sign you got right there, buddy. That would be spelled with an I right here, that type of complement. This type of complement means that they add up to 90 degrees. So if you have sine and you spell out the word, it looks like that. And then we have cosine and spell it out. You're thinking, what is this, an English class? I'm going to get to the point, hold on. And then we've got tangent is spelled like this. And then there's cotangent, which usually we just write COT. We've got secant, which we usually write as just SEC, and then cosecant. Well, notice all of these start with co, and so does this. So these are the cofunctions of sine, tangent, and secant. The complement of sine, the complement of tangent, the complement of secant. Mind blown. And the fact is, if A and B add up to 90 degrees, that sine of A will equal cosine of B. Oh, that was a sloppy B, sorry. So as long as A and B are complements, then the complement functions will be the same. That is what I just got right here. So you use the complementary functions, you'll get the same answer. And then for tangent of A, it will equal cotangent of its complement, and secant of A will equal cosecant of B. So this is called the Cofunction Theorem. And right now, I'm sure that you are getting out your 3x5 card and you're ready to write it down on the 3x5 card. Well, don't. So this is something that's used every once in a while, but not really enough that you need to. It's not card worthy. You don't have to have it memorized. We'll just use it every once in a while. Okay, then on to example number 2. So suppose that you have this triangle, and this is not drawn to scale, but let's say this is 20 degrees and this is 70 degrees. So then sine of 20 degrees equals, and cosine of 70 degrees equals. So this is just meant to be a very easy, fast example, basically showing you the cofunction theorem, but in a different way, using a calculator. So I don't have any sides on here, so I can't just use opposite and adjacent, etc. So instead, we're going to be just using the calculator. So make sure that the calculator is in degrees mode. Otherwise, if it's not, go to mode, change it to degrees, and then hit second quit. Okay, so how much is Sine of 20 degrees. It equals a 0.342. What about cosine of 70 degrees? So the cofunction theorem said that I would get the same answer, and sure enough, it's the same. So let's try secant of 20 degrees and cosecant of 70 degrees. Now remember, you can't use the same angle. They have to be the complement. So these two angles have to add up to 90, and then we should get the same answer. Well, my calculator doesn't have secant, so instead I have to use 1 over cosine. So 1 divided by cosine of 20 degrees equals a 1.064. And my calculator doesn't have cosecant, so I'm going to need to use 1 divided by sine of 70, and sure enough, those two are the same. So the cofunction theorem seems to be working. You know what, while we're doing this, I wanted to just quickly demonstrate something else. So in here, I was using 20 degrees and sine. What if, and again, I'm not trying this to scale, what if you double the angle? So right now, I'm just going to look at sine. So what happens if you double the angle? Does it double the answer? So what is sine of, oops, I already did that one. Sine of 40 degrees, and it equals a 0.643. Is that the double? 2 times 0.342? No, it's not double. It's sort of close-ish, but no, it's not double. Okay, what if I take this angle and I triple it? So now, change it to 60 degrees. What happens to sine? So what if I change this to 60 degrees? So sine of 60 degrees. Is it triple this answer? Let's see, sine of 60 is equal to a 0.866. Is that triple this? 3 times 0.342. Nope, that's not even close. It's not triple. Now, what's the biggest that this could get? Well, since these two have to add up to 90, so let's see, in this case, this would be 30 degrees right here. This would be 50 degrees right here. So basically, let's say this gets really small. If this is only 1 degree, and these two have to add up to 90, that means this could be 89. So again, I'm not drawing it to scale, because if I did, it would be very difficult to write the numbers in here. So what if this was 89 degrees and this was 1 degree? Then how much is sine of 89 degrees? Sine of 89 degrees, equals 1. That sort of surprised me because I know that the answer is 0.9999. So the calculator is rounding too much. Let me change the mode, and I'll change this to float. And what that means is the calculator will give as much accuracy as it can find. So then how much is sine of 89? So it's actually 0.999847, etc. So it's not that this doubles or triples, but as the angle gets bigger and bigger and bigger and closer to 90, this gets closer and closer to 1. So it must be that sine of 90 degrees equals 1. And right there, the calculator is giving me as much accuracy as possible. It's saying it's exactly 1. Okay, then on to example number 3. Find the exact value, which means don't use a calculator, don't use decimals, but your answers should be like 1 over the square root of 3 or something like that. So for part A, 3 sine squared of 30 degrees. Well, if it's going to be exact values, then it's going to come from one of these two triangles. And since it's 30 degrees, it's going to be this one right here. So then use the 30, 60, 90 triangle. 30 degrees, 60 degrees. Across from 30 is 1. Across from the 90 degrees is 2. And across from 60 degrees is the square root of 3. So this is going to be 3, and then something gets squared. And the something that gets squared is the sine of 30 degrees. So sine is opposite over hypotenuse. So it'll be 1/2 gets squared. So when you square 1/2, that equals a 1/4. So it equals 3/4. And there is my exact answer. Now to check it on the calculator. So 3 sine of 30 degrees, and then it gets squared. And it should equal 3/4. And the calculator is going to say it as a decimal. It should say 0.75 for 3/4. Or if you want to see the fraction, just go to math. And the first thing is, change the answer to a fraction. It equals 3/4. Then for part B, how about sine of 60 degrees plus cosine of 60 degrees, and then square the whole thing. Now there is this identity that sine squared plus cosine squared equals 1. But this one is different because this is saying add them together first and then square. And that is different than square each one individually. So you can't just distribute the square and say that means it's sine squared plus cosine squared, the answer equals 1. Because watch, at the end, the answer is not going to equal 1. Okay, sine of 60. So starting with the 60, sine is opposite over hypotenuse. So it's going to be the square root of 3 over 2. Now cosine. So start at the 60, and cosine is adjacent over hypotenuse. So that is 1 over 2. And then the whole thing gets squared. Well, it just so happens these already have a common denominator, so I could rewrite this as the square root of 3 plus 1, and then the whole thing is divided by 2. Then square it. So that means square the numerator and square the denominator. Now personally, I would just stop right there. But if you do need to multiply out the top. So this is a binomial squared. That means you need to square the first thing. And the square of the square root of 3 is just 3. Then multiply the 1 with the radical 3 and double the result. So that will make 2 radical 3. And finally, square the plus 1. That's plus 1. Well, then I have these common terms, the 3 and the 1 that I need to combine. So that would make 4. And at this point, I have to keep going because this has a 2 in it, this has a 2 in it, and this has a 2 in it. So since it appears in all three terms, divide by 2, divide by 2, and divide by 2. So finally I get 2 plus a radical 3 over 2. Okay, on to the last idea of this section, and that is an application. So if this is a horizontal line, and this could be like you're looking that way. You're looking straight across. So you're just standing on the ground and you're looking across. And then you see a squirrel in a tree, so you look up to it. So you look up into the tree to see the squirrel. So when you look up, this angle right here is called the angle of elevation. Because you had to elevate your head to look at it, angle of elevation. Then you go ahead and look straight forward, and then that squirrel jumps on the ground, and you think it's so cute that you keep watching the squirrel. So then you'd have to look down to the ground to see it, and then looking down like this, that's called the angle of depression. So to depress means to push down, so the angle got pushed down. Okay, for the fourth example. This person is 35 feet from the base of a tree. And because we can only use right triangles, we're going to assume that the tree is standing upright. It's not growing at an angle or falling down, it's upright. And then the angle of elevation to the top of the tree is 27 degrees. We can use that small amount of information to figure out how tall is the tree. So you don't have to make a fancy picture. This is going to be the tree, and I'll use h for its height. Like I said, we need to assume that this is a right angle, that the tree is standing upright. The person is over here, and then when they look up, the angle of elevation is 27 degrees. And they are standing 35 feet from the base of the tree. So which trig function uses opposite and adjacent? It does not use hypotenuse. Opposite and adjacent, that's going to be this one right here, tangent. So the equation will look like tangent of 27 degrees equals, the opposite is h, the adjacent is 35. Opposite over adjacent. And then we're almost done. Just multiply both sides by 35. And then type that into the calculator. So when you're doing this math right here, do not type this in a calculator and get a decimal and then put the decimal right here. It's more accurate to just use the word tangent of 27, type the whole thing in the calculator after you've done the algebra. So 35 tangent of 27. So the tree is 17.833 feet tall.